This video covers implementing digital circuits with truth tables and Boolean equations. Digital circuits can be used to implement Boolean equations using electronic switching theory. Boolean equations can also be represented using what is called a truth table. It is possible to go between these three logic representations without too much trouble. Additionally, you can use optimization techniques in the Boolean equation domain, truth table domain, or digital circuit domain to minimize the ultimate digital circuit. Let's start with a Boolean equation and try to find the truth table and the digital circuit for it. So, given a Boolean equation, f is equal to a and b and c, or a and c, or b prime and c, we can find the truth table. How many input variables do we have? 3, a, b, and c. So we have a total of 8 possible input combinations, or 2 to the power of 3 possible input combinations. So 3 inputs, 2 to the power of 3 input combinations. So what is the truth table? Let's list our input variables and our output variable first, a, b, and c, and our output variable f. I recommend listing your input combinations 0 through 7 in ascending order in binary. So 0, 0, 0, 0, 1, 1, 1, 1 for 8 possible input combinations. 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. And we can see, looking at the values of A, B, and C, that we have 0, 1, 2, 3, 4, etc., all the way up to 7, all listed in binary now. So let us take our Boolean equation and look at each term and see if we can find the value for f for each input combination. Let's look at a equals 0, b equals 0, c equals 0. So the first case here, a equals 0, b equals 0, c equals 0. So if a is 0 and b is 0, well, we know that if a is 0, that the first term here is going to be 0 and the second term is going to be 0. We also note that because c is 0, this is going to be 0. So 0 or 0 or 0 is 0. Let's look at our second value here, 1. 0, 0, 1. So, because a is 0, this term and this term are both 0. Here, in this term, the a is not included. Let's look at b. b is 0. 0 inverted is 1, ANDed with c, which is 1. So 1 and 1 is 1. So 1 or 0 is equal to 1. So we'll place that in our truth table here. Let's look at our next value, 2, or 0, 1, 0. So a equals 0. So we have 0 here and 0 here. b equals 1. Notice that b inverted for b prime becomes 0. 0 ANDed with 1 is 0. So 0 ORed with 0 is 0 again. And now we have a equals 0. So these are both zeroed out. b equals 1. 1 inverted is 0. So 0 ANDed with 1 is 0 again. So 0 ORed with 0 gives us 0 here. A is now equal to 1. So we need to look at the possibility for these two terms. However, C is 0. C is 0, so we can immediately discount all three terms. C is 0, ANDed with anything is 0. C, 0, ANDed with anything is 0. C is 0, ANDed with anything is 0. In fact, let's use a shortcut here. We know that for any possible value, any possible case where C is 0, this term is going to be, the f value is going to be 0. So let's just use a shorthand. So for here, 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 and here, we know that C is 0 and therefore f is 0 because all three terms have C equal to 0. Let's look at A equals 1, B equals 0, C equals 1. So we have B prime C here. B prime is 0, primed is 1, ANDed with C equal to 1, so you have 1, ORed with 0, ORed with 1. So you have 1 for 1, 0, 1. Finally, we have A equals 1, B equals 1, C equals 1 for this first term. So we have a 1 for A, B, C equal to 1, 1, 1 respectively. And this gives us our truth table. So a question now, how do we implement a digital circuit for this Boolean equation? Well, let's list out our input variables. A, B, and C. And then we also need a B prime. So let's place an inverter for B prime. And we will connect the B to the B prime through an inverter. Now we have three AND gates, A, B, and C. Let's draw an AND gate, connect it to A, B, and C. So A and B and C for this first term. Then we will look at A ANDed with C. So A ANDed with C for our second term. Finally, we need to AND, use an AND gate to connect B prime and C. Now these three terms are connected through an OR gate. So we have these two OR terms, so we can use a 3-input OR to connect them all. And finally, we have our output F. Notice that we have a total of 5 gates. Now, there are multiple ways to optimize for this, and we'll talk about primarily optimization of logic gates. So, looking at the equation again, how do we get an optimized Boolean equation? There are multiple ways to optimize for a Boolean equation to get a smaller digital circuit. Multiple targets. The target that we are going to use is minimal number of gates in this demonstration. So let's look at F equal to A, B, C, or AC, or B prime, C. Let's first do this. This term is equal to AC ANDed with 1. 1 is also equal to B or B prime. So we're intentionally making this more complicated. If we distribute, we get A, B, C or A, B prime, C for just this term. So let's write this out in complete form rather. A and B and C, or A and B and C, or A and B prime and C, or B prime and C. Now, we can see here that A and B and C combines with A and B and C, right? Because of idempotency. So, we can say that F equals A, B, C, or A, B prime, C, or B prime, C. So remember that Q ORed with Q is equal to Q. Because if Q is equal to 0, then Q or Q is equal to 0. If Q is equal to 1, then 1 or 1 is equal to 1. So Q or Q is always equal to Q. This is why we can get away with this change here and converting it to this term here. Finally, we remember that AC is equal to ABC or AB prime C. Notice that we have this term here still. So let's combine. F is equal to AC or B prime C. Now we can simplify further by using the distributive property to factor out a C. C ANDed with A or B prime, like so. Now that we have this, we have a very small equation, very compact. So before we had 3 terms that were ORed together, and each term had an AND gate. So now we have only a very compact form here. So let's take a look. If we draw this out, let's use longhand again, be very structured. A, B, C. And then we place an inverter here for B prime. Then we have one logic gate. Now we have to handle this OR gate first. So A ORed with B prime. Then we have this AND here, where we AND with C. Like so. And this gives us our final output, F. Now if we look closely, we have 3 gates. So we have very handily reduced the number of gates and reduced the size of the circuit. We can compare with our first circuit, which had 5 gates on implementation. So let's start now with the truth table. how do we implement the Boolean equation based upon this truth table? Well, a very nice property of truth tables is we can say that we can use the and or statements to describe it. So if A is equal to 0, and B is equal to 0, and C is equal to 0, then Y is equal to 1. So let's write that out. Y is equal to 1 if A, not A, and not B, and not C. Or A is equal to 0, A prime, B is equal to, and B is equal to 0, and C is equal to 1. So we don't prime it this time. Or Y is equal to 1, emphasizing or, A is equal to 1, and B is equal to 0, and C is equal to 0. Or A is equal to 1, oops, B is equal to 0, C is equal to 1, and C is equal to 1. Or A equals 1, and B equals 1, and C equals 1. So given a truth table with all of the 1s, Y is equal to 1 if and only if this is true, or this is true, or this entry is true, or this entry is true, or this entry is true. This allows us to create an and or network using a Boolean equation, similar to this. What does the digital circuit look like? Well, let's draw it out. We have 3 variables, A, B, C. How many of these variables are inverted? Well, we can see from the first term over here that all 3 of them are inverted, so we're going to need 3 inverters. So we can get A prime, B prime, C prime. So let's connect A prime, B prime, and C prime. Now, how many entries do we have? We have 5 entries in this truth table. 5 1 entries, so we're going to need 5 AND gates if we're blindly following the digital circuit generation algorithm. 1, 2, 3, 4, and 5. A prime and B prime and C prime for the first term. Our second term, A prime, B prime, and C. Our third term, A, B prime, C prime. Our fourth term, A, B prime, C. That was done, and now we have our fifth term, A, B, C. So we have our AND gates. Now what do we need? We need to OR them together. So we need a 5-input OR gate. Let's create a 5-input OR gate. Like so. And now we have our output Y. So, given this truth table and the Boolean algebra equation that we generated from it, how do we optimize the Boolean equation? And how do we find the optimal digital circuit? Well, let's start with the Boolean equation first. So, this is copied from the previous slide. So, let's take a look. A nice thing about these terms is we can use Boolean algebra theorems to reduce these. A prime, B prime, and C prime can be combined with A prime, B prime, C here and here using the distributive property. Another thing that we can identify is that A prime, B prime, and C prime can be combined with A, B prime, C prime, and C prime as well using the distributive property. Unfortunately, we're unable to combine one term with two terms at the same time directly. However, using idempotency, it's possible to duplicate this term and reap the benefits. So let's take a look. Let's use the idempotency property to duplicate A prime, B prime, and C prime, ORed with A prime and B prime and C prime. We're just using idempotency to duplicate this. Now I'm copying the last four terms as follows. A prime, B prime, C, ORed with A, B prime, C prime, ORed with A, B prime, C, ORed with A, B, C. Now, why would we increase the number of terms and make it more complicated to reduce? Well, let's take a look at what happens when we combine terms. So this first A prime, B prime, C prime term combines with A prime, B prime, C. So factor out A prime, B prime, and you get C prime or C. We'll take A prime, B prime, C prime, and A, B prime, C prime, and we'll factor out B prime and C prime from A prime or A, and we get this term now. We can now copy these remaining terms here. Notice that we can factor out an A and C from both of these terms as well. So we get A and C ANDed with B prime or B. Now, very interesting, notice that K ORed with K prime is always equal to 1. If K is equal to 0, then K prime is 1, and that's equal to 1. If K is equal to 1, K prime is equal to 0, or together is equal to 1 again. So we can minimize our Boolean equations like so. A prime and B prime, or B prime and C prime, or A ANDed with C. So quite a bit smaller now. So let's draw the digital circuit. We have A, B, C, and we need inversions of all three variables, so 3 inverters again. And then we get A prime, B prime, C prime. We have our layout here, and we need 3 AND gates for 3 terms. So let's start with A prime, B prime. Covers this term here. Then we'll do B prime or C prime. B prime and C prime, excuse me. And finally, we'll do A and C. A ANDed with C. And we can OR these 3 inputs together. Now, if you're familiar with transistor logic, or the transistor implementation of this logic, you'll know that a 3-input OR gate is inherently smaller than a 5-input OR gate just based on the number of transistors. So you can use the number of transistors as an optimizing target as well. But looking here, you have 3 inverters, 3 AND gates, and an OR gate. So we have, instead of 9 gates, we have 7. So we have a reduction of 2 gates from the previous implementation in a digital circuit. So let's start with this digital circuit here. What is the Boolean equation here? Well, we have F is going to be equal to something. So we have one term here, A prime ANDed with B and C. That's primed. And that is ORed with A prime. And this is ORed with another term, D prime, ORed with A prime, B, C. So you have D prime, which comes from here, this OR symbol here, and then you have A prime, B, C. Like so, at this node. A prime here, D prime, A prime, B, C, quantity prime, and then you can get your NOR gate, A prime ORed with A prime, B, C, quantity primed, ORed together as primed, ORed with this value here. Finally, you get F. So we have 4 variables here. So with 4 variables, we have 2 to the power of 4 equals 16 combos, 16 input combinations. Let's write them out. A, B, C, D, and output F. 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. 16 possible combinations. We're going to draw some separator lines here just to help with our formatting and make sure everything is aligned. So now we say 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, alternating 2 zeros and 2 ones for C. And then for D, alternating 0, 1. So for 16 possible input combinations, we have binary numbers 0 through 15 listed in order here. So now what is the truth table? Well, we need to plug in for each of these possible input combinations, which could take a little bit of time here. In this case, I recommend optimizing the Boolean equation first and the digital circuit before going to the truth table, because it will minimize the amount of work you need to do when actually generating the truth table. Remember that the optimized version of a Boolean algebra equation and the unoptimized version of the Boolean algebra equation are equivalent. They will have exactly the same truth table. So what does the optimal Boolean equation look like? Well, let's place this equation here, and let's look at the Boolean equation. Looking closely here, we know that this prime can be distributed using De Morgan's law. So let's do that. So when we distribute the prime, or becomes and. So we have A prime, B, C, double prime, ANDed with A prime, prime. ORed with, and now for this term we can drop the parentheses. So we will say D prime or A prime, B, C. Notice now that we can say that these double primes cancel each other out. An inversion of an inversion is a constant value. So A double prime equals A. So this double prime cancels. We get A prime, B, C, ANDed with A, or D prime, or A prime, B, C. Now here's something interesting. Equal to A prime, B, C, A, or D prime, or A prime, B, C. This equation has a term where A prime is ANDed with A. A prime ANDed with A is equal to 0. A prime A equals 0. Why? Because if A is equal to 0, then A prime is equal to 1, and so this is equal to 0. If A is equal to 1, therefore A prime is equal to 0, and so ANDing those two together is 0. Therefore, A ANDed with A prime is always equal to 0. So this simplifies, after cutting to 0, this simplifies to D prime or A prime, B, C. So let's bring this back to our truth table here. Let's go ahead and fill this out. If D is equal to 0, then D prime is 1. So if D is equal to 0, D prime is 1. 1 ORed with anything is equal to 1. So when D is 0, F is always equal to 1. Let's fill in all of these entries then. 1, 1, 1, 1, 1, 1, 1, 1. Now, let's look at this other term here, where a prime and b and c is equal to 1 and d prime is 0. So when d prime is 0, d is 1, so we're looking at all the other 8 possible combinations. We've already covered half of them with one term. So if a is equal to 0, and b is equal to 1, and c is equal to 1, then f is equal to 1. So let's look for the place where a is equal to 0. So it's one of these 8 possible combinations. And where does b equal 1 and c equal 1? At this location here and this location here. So we'll place a 1 here, and we already have a 1 for the first entry. All other entries are not covered by either the d prime or the a prime or b and a prime and b and c term. So we are going to list zeros for the rest. And so we have a truth table here for this digital circuit. We also have the unoptimized Boolean equation, and we now can develop an optimized digital circuit. Notice that f is equal to f, so regardless of how we implement our digital circuit or Boolean equation, how we represent the Boolean equation, whether it is optimized or unoptimized, the truth table is always the same. So when we look at this statement here for optimized truth table, it's constant. If your truth table changes, you have an error. So let's look at our Boolean equation here. Let us create an optimal digital circuit for this one. So we have input variables A, B, C, D. Let's label them. We also need 2 inverters for A prime and D prime. A prime, D prime. And so we can create one AND gate for A prime and B and C. We could also create a gate for D prime as well. That would be another AND gate term, but D prime is not ANDed with anything, so we can route that directly to an OR gate. So D prime ORed with A prime and B and C. And this gives us our final output F. So we have significant simplification. We go from 2 inverters, an AND gate, and an OR gate when we start with this complicated circuit here. So some takeaways that you should keep in mind. Logic minimization is hard. So if you are a computer scientist, you may know about complexity classes. 2-level logic minimization is NP complete, and multi-level logic minimization is quite a bit harder. Modern CPUs, microprocessors, your computer chip, will have millions of logic gates, so perfect optimization is impossible. However, near-optimal solutions are possible to find for many digital circuits. So looking for the optimal circuit will take you an infinite amount of time. Well, or near as enough as makes no difference. However, using the techniques that you've learned here in this video, it is possible to reduce the logic circuits significantly.